Hello everyone, I'm Sevda. In this video, I will examine an airbending operation performed on an aluminum sheet as a representative engineering problem. Airbending is a process in which a sheet metal workpiece is pressed into a die while an air gap remains between the bottom of the sheet and the die. This gap is the origin of the term airbending. This method is most commonly used when production speed and flexibility are more important than high precision. This study prepared as explain the engineering fundamentals of the sheet metal bending process. Particular emphasis is placed on material behavior, the Springback effect, and the process of theoretical, experimental, and numerical validation. From an engineering perspective, the sheet metal bending process can be examined in four main stages. In the first stage, material properties and geometric parameters are defined. In the second stage, the theoretical calculations are performed to predict material behavior and the Springback effect. In the third stage, experimental bending is carried out using the determinate parameters. In the final stage, the process is validated through numerical simulation. In the study, all four stages were applied systematically. The success of the bending process largely depends on the accurate definition of material properties. In the study, the aluminum sheet thickness is 1.5 mm. Mechanical properties such as the elastic modulus and yield strength form the basis of the theoretical calculations. Another parameter that must be emphasized here is the rolling direction. During manufacturing, sheet metals are formed by passing them between rollers, causing the grains in the microstructure to elongate in a preferred direction. If the bending operation is performed parallel to this grain direction, meaning the sheet is bent along the rolling direction, the ductility of the material decreases and the risk of cracking increases. This effect is particularly pronounced in aluminum alloys. To reduce risk, the bending axis was selected perpendicular to the rolling direction. In addition, the internal bend radius was chosen as twice the sheet thickness. This selection allows the tensile stresses on the outer surface of the material to be distributed more evenly during bending and reducing the risk of cracking. One of the most significant physical effects encouraged in air bending operations is springback or elastic recovery. During bending, the material undergoes both elastic and plastic deformation. When the applied load is removed, the elastic portion of the deformation recovers, causing the bent part to open slightly. For this reason, springback is not an error, but a predictable material behavior that must be taken into account. In the study, the target final inner bending angle was 105 degrees. Based on theoretical calculations, a springback was approximately 0.5 degrees was predicted. Therefore, the part was initially bent to smaller angle under load. After the unloading and springback, the part reaches the desired final angle. At this stage, additional checks were performed and a geometric clearance calculation was carried out. The result confirms that the process was conducted under true air bending conditions. All parameters determined through theoretical analysis were applied experimentally using a press brake machine. The purpose of this stage was to observe how accurately the theoretical calculations translate into particular results. After the experimental bending operation, visual inspection alone is not sufficient. Therefore, a high-resolution image of the bent part was taken, and a digital angle measurement was performed using imagery software. This method improves measurement accuracy and reduces human-related errors. And the measured inner bending angle was found. The measured result was compared with the target angles. According to calculation, the deviation was only 0.45%. This value falls within the specified tolerance range and indicates that the experimental application was successful. In the final stage, the bending process was numerically modeled using ANSYS. The purpose of this step was to validate the experimental results and to evaluate the repeatability of the process. In the simulation, material properties, rolling direction, and springback settings were carefully defined. The final inner bending angle obtained from the simulation was calculated. During the calculation, the alignment of the selected measurement points and the direction of point selection are critical. Otherwise, an accurate angle value cannot be obtained. In addition, stress concentration at the inner band radius region during bending is clearly observed at the right. When the theoretical target, experimental measurement, and the numerical simulation results are evaluated together, a comparison among the three approaches is obtained. The result supports the accuracy of both the theoretical model and the numerical simulation. The main engineering lessons derived from this study are as follows. Method integrity must always be property, and rolling direction must be taken into account. Springback is a significant physical effect that should not be neglected and must be calculated. Reliable engineering results are achieved when theory, experiment, and simulation are evaluated together. In conclusion, all the sheet metal bending may appear to be a single operation. It requires detailed engineering analysis. I hope this presentation will be helpful for students who wish to better understand the sheet metal bending process. Thank you for listening.